In this video, we'll talk about decision tree and random forest intuition. So let us first start with decision tree. A decision tree predicts a binary or multi-class outcomes using a sequence of true-false or yes-no rules. For each variable rules in the decision tree, one independent variable is selected and the training is divided into two groups. The aim is to split the data in a way that each group represents a single value of the categorical variable you are trying to predict. This helps in making accurate prediction. A decision tree follows a set of rules to split the independent variable, which are used to classify the dependent variables into different classes. The process evaluates the effectiveness of the splitting process using a matrix called entropy. We will discuss entropy later in the video itself. Please note that the process we are about to discuss is machine learning and not a manual process. The computer or the decision tree will perform this process multiple times and then select the optimal rule to divide your data and isolate the classes of your dependent variables. The change in the matrix, which we will discuss in entropy, from before the split to after the split is called information gain. The whole idea behind a decision tree is to split the dependent variable into certain groups, and most of these groups should belong to a single class of your dependent variable that you are trying to predict. Entropy and information gains are useful tools to achieve this objective, and I will explain what they are and how they work. Decision tree are type of classification method that are useful for predicting customers' behavior, such as cancellation, churn, upgrades, cross sales, or even advanced scenarios like identifying fraudulent bank transactions. So this is just a brief summary. So let us dive deep into this algorithm and see how it actually works. So we have a list of independent variables including age, gender, household income, sign-up date, last login, and lifetime value. Let us take an example to understand how decision tree works. It is crucial for subscription-based business to predict customer churn. Therefore, our aim is to predict if a subscriber will churn next month. So we have a data set of 20 customers with 10 who have churned and 10 who have not churned. Let us divide this data into two categories based on gender of the subscriber. We'll group all the males in one bucket and all the females in another bucket. So it is observed that splitting the data by gender doesn't prove to be useful in predicting the outcome for both groups. The number of subscribers who churned and who didn't churn remains the same. Therefore, gender cannot be considered as a reliable predictor at this stage of the decision tree. So now let us split on last login based on whether the subscriber logged in less than or more than 7 days. So it appears that data has been divided in a useful manner. On the right side of the split, there are 7 subscribers who have churned and 1 who has not. On the left side, where the duration is less than 7 days, 4 subscribers have churned and 8 have not. So last login seems to be a good split to predict if somebody will churn or not. So how we can determine which independent variable to split on? Do we have to manually test them one by one? We require a clear and concise matrix to assess the effectiveness of the splits in dividing our dependent variable into two distinct classes. So entropy is the measurement. Entropy is a measure of level of evenness or uncertainty in a dataset. For example, if we have a dataset with 7 yes and 1 no on the right hand side, there is a very little uncertainty regarding the classes of the dependent variable. Therefore, the entropy would be low. However, before the split, there is high entropy because we are not certain which class is in that data. So do we manually calculate the entropy for each split? Of course not. Machine learning is a process that involves testing various independent variables against different rules to predict and classify outcomes. The process involves measuring entropy before and after splitting data to determine if the entropy decreases and the certainty of the classification increases, leading to accurate prediction. So let us explore how the entropy is calculated and applied to a full decision tree, not just one split. So the question is, how do we actually calculate entropy? So let us break down the formula, even though it seems daunting at first. In this formula, P represents the probability of class 1. Therefore, it is calculated as the count of class 1 over the total number of observations. Here is the probability of class 2, which is the count of class 2 divided by total number of observations. The total number of observation is simply the capital N. The log base 2 turns this probability into a smooth curve which will range from 0 to 1. The graph we are looking at has two axes. Y-axis measures the entropy and x-axis measures the probability of classes. Since we have only two classes, the probability adds up to 1. As the probability of class 1 increases, the probability of class 2 decreases. And this happens until the probability of class 2 is 0 and the probability of class 1 is 1. The entire range of probabilities for class 1 and class 2 is represented on the x-axis. When we look at the point on the x-axis at 0.5, we find that the probability of class 1 and class 2 is equal, so that is 50%. This means that the entropy is at its maximum level. Entropy is the measure of uncertainty we have about the classes in the data we are analyzing. When the classes are equally split, that is 50-50, it results in maximum uncertainty or maximum entropy of 1. If we divide our data into classes and all the values in the classes are the same, then the entropy on that axis will be 0. This means that if we plug in P1 equal to 1 in our formula and P2 equals to 0, our entropy calculation will be 0. The same thing applies to when the probability of class 1 is 0 and all classes are class 2 on the left side of the axis. So this is how entropy looks by itself. So let us go back to our decision tree and observe the entropy calculation in action. So we are working on predicting whether the subscriber will cancel their subscription in the next month. To accomplish this, we have split the data into two groups based on a rule. So subscribers who logged in more than 7 days ago and those who logged in less than 7 days ago. We have determined that this split is better than using a gender as a predictor, but still not perfect. We have to perform calculations to analyze our data further. So here are the entropy. The entropy at the top is equal to 1 because there was a 50-50 split in the class, just like what we have observed in the curve. On the bottom right, the entropy is 0.54, indicating the decrease in entropy from its previous value of 1 down to 0.54. So there is a decrease in 0.46. So this decrease in entropy signifies that we have gained lot of information and certainty about the classes in this split, based on the rule that last login was greater than 7 days ago. We can split again to get more information gains or more drop in entropy. So let us divide the lifetime value into two categories based on the value being less than $50 or greater than $50. On analyzing the data, we observed that there was a slight increase in the value for greater than $50, but no significant change for less than $50. On the right hand side, we made a split based on age with one branch for individuals younger than 35 and another for those over 35. So as a result of the split, the entropy of each branch decreased to 0. So it is important to note that these splits are not made manually when building a decision tree. The computer handles this process automatically. However, this is the underlying mechanism behind decision tree construction. So here is our next example. We have a decision tree that predicts the churn of 20 subscribers. We split the trees based on the last login and move towards the right side. On the right side, we further split based on age. We then split based on lifetime value and sign up date on the left side. The purpose is to create rule that can divide our dependent variables into groups using independent variables. So this process is iterative and we aim to achieve successful segmentation based on the class of variables. So we have a customer who is 52 years old and hasn't logged in for 21 days, which is quite a long time. To predict, simply follow the decision tree rule starting from the top. So I can see that the user's last login was over 7 days, which means they are listed on the right side. Additionally, they are 52 years old. So we will move further down to the right side as they are over 35 years old. So based on this information, our prediction is that the answer is yes, they will churn because what we have seen consistently in the data as defined by the decision tree. In decision tree, we use some specific terms. Each group we split is called node. The root node is the first node at the top of the tree. When we split a node, it becomes a decision node. The final split node or node in the tree is called a leaf node, where there can be no more splits after that. So this is where we get our prediction, just like the example we saw earlier with the 52-year-old customer whose last login was 21 days ago. Let us consider another example using the same decision tree. So suppose we have a customer who signed up 90 days ago, logged in 3 days ago and has an LTV of $28. So we followed the path where we moved to the left because the user logged in less than 7 days ago. Then we move to the left again because their lifetime value is less than $50. Their sign up date was greater than 60 days ago, so I'll move to the right this time, and this is that leaf node, and we can see that 3 out of 4 people did not churn. Therefore, our prediction is that the subscriber will not churn. Let us take one more example. So we have a subscriber who logged in 5 days ago with an LTV of $70. So you can follow the path down to the leaf node. Logged in 5 days ago, so right side, and LTV of $70, so the left side. So there are 5 no churns and 2 churns, so therefore we'll predict no churn. So perhaps you have a question about when we should stop dividing. Splitting data excessively can result in overfitting. To prevent this, you can modify the input of the decision tree models by limiting the depth of the tree, that is the number of layers of split, or the leaf size. If a split results in too few observations in one of the leaf node, the leaf size can be adjusted to avoid overfitting. So here I wanted to mention something about overfitting. When you are training a machine learning model, you will be adjusting certain parameters like tree depth or leaf size, which are called hyperparameters. So these are the levers you will get to pull to ensure that your model is working well and not overfitting or underfitting. So it is important to keep an eye on the test data versus the training data to avoid overfitting. You may be wondering how we determine the best way to divide numerical independent variables. When dealing with binary independent variables, the split is straightforward, a simple yes or no. However, with numerical variables, there are many possible split points. Decision tree will examine multiple split points and choose the one with the highest information gain. The number of possible split points to evaluate is a hyperparameter that can be adjusted. Now you may be thinking that the most significant information gain or largest drop in entropy on the first split may not always lead to best model. So this is a fundamental flaw of decision tree. However, decision trees are still a reliable tool in machine learning classification methods. So one way to handle this flaw is to train numerous decision trees, which is commonly known as random forest. So random forest consists of decision trees that uses a random set of observation and variable to split on at each split. In a random forest, each decision tree will randomly choose a subset of the columns. At each split, we randomly select a set of variables to split on, and this allows us to try out many different combinations of variables to split on. Unlike a decision tree, which may always choose the most information gain in the first split, a random forest guarantees exploration of all possible outcomes, therefore eliminating biases. Now, how do we get the prediction? Well, each tree produces a prediction and then the mode or most occurring of all those predictions are taken up and it becomes a final prediction. A random forest is widely used technique in applied machine learning for business intelligence. It involves a set of decision trees created based on subsets of observations and random subsets of independent variables for each split. The final prediction is made taking the winner of the voting of all the decision trees. Thus the name random forest. And this is all about the decision tree and random forest, and in the upcoming video we'll do some practical assignments as well, so stay tuned for that. And also subscribe to my channel if you have not done yet, and I will see you all in the next video. Until then, keep thinking data science.